Okay, let us start. So here, what happens is that today we'll be starting the next unit. Okay, so the next unit is basically T-beam and bridge deck. Okay, so here we'll have three methods basically. So a typical T-beam deck slab generally comprises the longitudinal girder, the continuous deck slab. Okay, listen one thing. I hope anyone from okay, so I have what I did is I have circulated the numericals that we did in the last classes. Huh? So there are certain two PDFs of that. So I have circulated it to Michael. So please collect it from Michael. Okay, I'm telling to everyone. Now, a typical TB deck slab generally comprises of longitudinal girder, a continuous deck slab between the T-beam and the cross girders to provide lateral rigidity to the bridge deck. Okay, so these are the two things basically that a T-beam bridge comprises. Now, my voice is breaking. Is it clear now? Is my voice clear now? Yes. Okay, fine. What about others? Are you able to hear my voice? Someone said that my voice is breaking. Yes. Yes. Okay. Okay. Fine. So, in T-beam bridge deck, we have generated three methods. So, for the longitudinal girders are generally spaced at intervals of 2 to 2.5 meter, and cross girders are provided at 4 to 5 meter. This is meter, okay? Printing mistake. Intervals. The distribution of live loads among the longitudinal girders can be estimated. Now, the live loads or the dead loads. All the loads distribution can be estimated by Carbon's method, Gaon-Massonet method, and Henry-Jaeger method. Now we'll basically do the Carbon's method only, okay? Because this is the most simple. Doesn't the calculations are long? I don't say that, but then from understanding point of view, this is simple, okay? So in Carbon's method, the ratio of span to width of deck is greater than 2 but less than 4. The longitudinal girders are interconnected by at least 5 symmetrically spaced cross girders. The cross girders extends to a depth of at least I'm again having network issues. Is my voice breaking again? Is my voice cracking again? Someone please respond. Is my voice cracking again? Voice not coming. Okay, okay, yeah. Things is cracking, no? Can we do wait? This Wi-Fi is not okay. Give me a minute. Is it okay now? Is it okay now? Is my voice? Can you repeat? Okay, I'll repeat again. I'll repeat again. Very first. Is it okay now? Is my audio okay now? I'll repeat. I'll repeat. Is my audio okay now? Can anyone please respond? I'll repeat again. Is my audio okay now? Yes. What about others? Is my audio okay now? Yes. Okay. Okay. Thank you. So let us repeat it again. So now in T-beam and slab based take, there are basically three methods: carbon method, Aeon Masonite method, and Henry Jaeger method. Now, a typical T-beam slab deck generally comprises the longitudinal girder, comma, the continuous deck slab between the T-beams and cross girders to provide lateral rigidity of the deck. Now it consists of two parts: longitudinal girder and a continuous deck slab, which is between the T-beams and the cross girders that are used generally to provide what? Lateral rigidity to the bridge deck. And the longitudinal girders are spaced at intervals of 2 to 2.5 meter and cross girders 4 to 5 meters. Fine. Now the distribution of live loads among the longitudinal girders can be estimated by three methods. Now let us discuss Carbon's method. Okay. Now in Carbon's method, what happens is that the ratio of there are certain criteria. Fine. So in this criteria, the ratio of span to width of deck slab is greater than 2 but less than 4, first of all. Then the longitudinal girders are interconnected by at least 5 symmetrically spaced cross girders. Okay. The cross girders extends to a depth of at least 0.75 times the depth of longitudinal girders. These are the most important, criteria. Fine. My voice again. What happened? Can't you hear my voice again? Yeah, I know it is breaking in the middle, right? Sorry for that, but I'll plus with the network. Actually, I don't know what is happening to the network. But, we can hear, but while you're explaining, the audio stops at times. Okay, I'm sorry. Let us see if it stops. Then I'll go it a bit slow and I'll repeat it again. You have to take the class. I hope it's clear. So the carbon's method is popular because of the simplicity of calculations. Now, when the live loads are positioned near to the curve, that means this is the curve. Curve means what? The raised portion of that slab towards the edge. That is known as curve, right? When the live loads are positioned nearer to the curves, as shown in figure like this, the center of gravity of live loads act eccentrically with the center of gravity of the girder system. Due to this eccentricity, the loads shared by each girder is increased or decreased depending upon the position of the girders. This is calculated by Carbon's theory by reaction factor. Now, in Carbon's theory, what happens is that suppose these are the two wheels of the vehicle, this one and this one, right? So now this will have certain eccentricity, that means E, which is from the center of the girder. Okay. Now these values are basically, what do you call it? These values are basically you know standard values because this is coming from that load pattern and all. Now this 1.2 meter is the distance of the wheel from the curb, and depending upon the position of the girders, depending upon the position of the girders, here is the diagram as per Turban's theory. Now if you see the diagram here, okay, Rx is the reaction of the girder under consideration. Okay, so Rx is the main reaction. I hope now the audio is clear a bit. I hope the audio is clear for you now. Yes, yes. Okay, okay, okay. So here, what happens is that Rx is the reaction factor of the girder. I is the moment of inertia of its longitudinal girder. Dx is the distance of the girder under consideration from the central axis of the bridge. So this is the central axis. This is the central axis. Okay. So dx is this one. That means this part. Okay. So W is the total concentrated live load. That means W. E is the number. N is the number of girders. So here N will be 2. I'm just giving you an example. Okay. Now E is the eccentricity of live load with respect to the axis of the bridge. Now look, this is the axis because this is the neutral part, central axis. Now E is what? This is E, and this E is what? Basically the eccentricity of the live load. Now the live load bending moments and shear forces are computed for each of the girders. The maximum design moments and shear forces are obtained by adding the live load and dead load bending moments. The reinforcements in the main longitudinal girders are designed for the maximum moments and shears developed in the girder. These are the design parameters that are used for designing. Now, these numericals are very long actually, this carbon theory. So, first of all, let us take the question. I hope this question is visible to all of you. I'm zooming it again. I hope this question is visible to all of you. Please take the screenshot of this question. Please take the screenshot of this question. So these are the data that is given actually. Now let's go the data. First of all, effective span of T-beam bridge is given 16 meter. Now the width of carriageway is 7.5 meter. Thickness of wearing put is 80 mm and 25 bed of concrete and F 415 HRG bars. And these permissible stress values, these are found from that previous numerical. I gave one table, right? For M25, these are the standard values of permissible stresses. So these are found from there. Now we'll be finding out the. Now here, if you see, first of all, the cross section of the decks. The main girders are provided 2.5 mm center to center. The thickness of the deck slab is 200 mm. Bearing code 80 mm. These are the data that is given with your main girders. Now depth of main girder is equal to what? The maximum data you will have to assume. First of all, the curves. Now, three main girders are provided at 2.5 mm centers. Now, why three main girders are provided at 2.5 mm centers? This is because if you see the question, the clear width of roadway is 7.5 meter. That is why we are providing three main girders at 2.5 meter center to center. Okay, so the three main girders will be provided at 2.5 meters center to center. Now the center thickness of the deck slab, this is 200 mm. This is what we generally consider. The wearing port 80 mm, we know. The width of main girders 300 mm, that is assumed. Most values you have to assume it like this. Okay, and these are almost the standard values. So in exam, if this type of question comes also, just consider these values only. Now, if you see the curves, the curves are what? 600 mm wide by 300 mm deep, and cross girders are provided at every 4-meter intervals. These are the specifications that we studied just now. Breadth of cross girder is 300 mm. Okay, and these are the certain what you call it design parameters. Fine. Now the depth of main girder will be 160 centimeter. Now for per meter one span, it will be 10 centimeter per meter of span. Therefore, the span is given as 60 meter. So it will be 160 centimeter. These are certain thumb rules that we have to consider. Now the depth of cross girder, this is taken equal to what? Depth of main girder to simplify the computations. Depth of cross girder is equal to depth of main girder. Also, after assumption, all these assumptions, we have come to these diagrams. I hope this is clear for everyone. You can take a screenshot of this diagram. So considering all the assumptions and everything, okay, we have basically come to the conclusion that this is the diagram. Hmm. Just take a screenshot of this.
Hello, sir.
Yeah, please carry on.
I have a question, sir.
Yeah, sure.
Sir, apart from exams, sir, there should be like how do we assume? We just they're assuming so many values. Like there should be a way which we should like have idea on how to assume this depth, breadth, because
Yeah.
sir, it's getting confusing.
Okay. Which part is getting confusing? Now look.
So like so many values are just assumed. Like there should be a process in where we can assume the breadth, maybe depending on the length, or but they just assume like I don't get how they just directly assume values. So is there any concept behind this assumption?
Mm, wait. Give me a minute. Tell you. If you see the first part, okay. If you see this first part, the ratio of span to width of depth. These are the three criteria that should be actually satisfied. Okay. Now here in this part, this 2.5 meter centers, I hope this is clear, this is not assumed. The thickness of deck slab, generally what happens? For our slab, it is 150 mm, right? In the concrete cases. But this is a bridge structure, so we have increased it 50 mm more. That is why it is 200 mm. Now, wearing code is always 80 mm. You all know it from the main. Now, width of main girders. This width of main girders, these are considered as 300 mm. And considering that value only, we have designed it so that we can check it whether our conditions that we are thinking it, these are correct or not. I hope this is clear now. Only this thing we have assumed. Curves and width of main girders. Rest all are like we have been doing it in the last numericals. I hope it is clear for you.
So that depth of main gather 160 centimeter at the rate 10 centimeter per
Hmm.
span. So I
Yes,
didn't
yeah,
understand that.
yeah, yeah. I know, I know. Now this is written somewhere. Wait, I can find out that statement. Wait, I'll show you from some codes and all. Wait, let me see. Actually, this is considered in that manner itself. I could not find it where it is written actually, but we have been studying it in that way. I'll let you know, okay, if I find out. Is it okay, Michael?
Okay, sir. Okay, sir.
Yeah, yeah. I'll let you know. Fine. Uh, as of now, we just do it in this way. Now, this is the cross section of the dick. Okay, this is basically the cross section. Now, we'll have to go for the design of interior slab panels. So, first of all, let us find out the moments. How to find out the moments? So this can be find out by using what? Carbon's theory. So, in Carbon's theory, this interior slab panels part it can be done not by using Carbon's theory but the picot stuff. The Carbon's theory will be coming from longitudinal girders. Okay. Now, in interior slab panels, what happens is that look at this. The bending moment initially the dead weight of slab. We have considered unit dimension of the slab and then we'll be designing it for the whole slab. Okay. We will be considering unit dimension. Then for unit area, we will be getting the dead weight of slab. Now, if you get the dead weight of slab per unit area, then only it will be acting as a why we consider unit area because the unit area is considered for this so that we can get it per meter square. This per meter square thing is coming only because of that unit area that we are considering. Okay, then only we can that for particular 1 meter square this is the dead weight of the slab. So this much for this much meter square we'll have to find out. So after that, this is one by one, and then 0.2 into 2.4. 0.2 is the thickness, and 24 is the what unit weight. Now for wedding code also, 0.08 into 22. I hope this is clear. Now we find out the total dead load as 6.56 kilonewton per meter square. Now the live load is IRC class double track vehicle. If you see the above diagram, in the very first one, these wheel dimensions, are 85 what 85 I mean 0.85 meter, right? Now this 0.85 meter means what? This figure or this wheel dimension resembles to IRC class AA loading. That is why this is IRC class AA loading. Okay. Now this is IRC class AA loading and this is IRC class AA track vehicle. Okay. Now this track vehicle will have, so we have to consider we have to find out what small u small v and then MA, ML and MB just like that we found out in the last classes. Like you will be getting then B, V, then U by B, then V by L, then K, referring to Pigot's curve, we'll be getting what? Small m1 and small m2. Then this MB and ML, we'll have to find out. So in this way, we'll be able to find out the capital M, MB and capital ML from small u and small v. Now, just think or consider one thing. We'll have to give this impact and continuity factors, which are what? 1.25 and 0.8 times. Okay, which are 1.25 and 0.8 times. So once we find out the MD and ML, then we'll have to multiply it with 1.25 and 0.8, so that we considered both the impact and the continuity factors. Okay, I hope this is clear up to this part. I hope this is clear up to this part. Since I explained these things in the last class, this MB and ML part, I think so all of you can find it out.
Hello, sir.
Yeah.
So that impact and continuity factor.
Impact and continuity. Yes.
The impact factor is for life load, right?
No. Yeah. Impact factor. Wait. Impact factor is actually for light load. Okay.
So,
And
but
now,
here we're considering moment of dead load.
yeah, we know that we are considering for dead loads, right? Definitely, we are
Yes, yes.
considering as dead loads. But then, what happens is that if uh, the vehicle, now we are not designing it for the live load, I know that. But then, what will happen? There will be certain impact values in T beam bridges for, you know, when the vehicle comes actually. That is why we are considering the impact factor. Okay, there will be certain impact. That is why we are considering the impact factor. Now, this is a particular T-beam bridge. And the previous classes, we just discussed regarding slabs, right? Simple slab designs. That is why in the dead load part, we did not consider any impact and continuity there. But here we'll have to consider impact and continuity. I hope this is clear. I hope this is okay for you. Is it
Yes,
okay
sir.
for you?
So
Hmm.
how do we get those values? Is it from IS code, those 1.25? Are they standard values?
No, there are not much codes. In bridge design, you don't find any codes. Maybe Indian Road Congress, there are certain rules laid down by it, which because of which you get this IRC class A, class AA. IRC, that Indian Road Congress codes that will give you, but IS code won't give you anything for bridge design. Okay, for the standard loadings and all, is Indian IS code means IRC gives you certain one. Okay, is it okay?
Yes, sir. Yes, sir.
So let us do one thing. The shear force part we'll be discussing in the next class, and eventually we'll complete this numeric in the next class.
Hello, sir.
Yeah.
So in previous class we discussed about slab bridges, and
Mm-mm-mm.
now, so how do we know like when to go for slab or T-beam? So is it depend on the span? Like how do we know when to decide if it's slab, we should design for slab or T-beam?
Okay, okay. Good. Wait, give me a minute. Say. Now, if you see in the dimensions, that is the span, okay, the clear span. If you see, in this clear span case, what happens is that if you see for the slabs, the span is very small, but for bridge, the span is like it is more than the clear width of the roadway. Okay, so that is then we just consider it as a T-beam bridge. Like, that means if you see the variations in the width of the slab, in a slab what happens now for a slab thing, we don't need to design the girders or we don't have to consider the dimensions of the girders. Just simply design the slab as per IRC loads. Fine. But and if you see the dimensions in the questions also, but or anywhere, the width of carriageway and the slab, in a clear span, it is lesser. But in case of bridge stakes, it is more. It is very high, more than double. In fact, are you getting me?
Yes, I got some.
Ah, you got it, no? Okay,
Yes,
okay.
sir. Thanks,
Just
sir.
check the variations of the, you know, I guess you have the questions. So in the questions, you can just check the variations of the what you know that what do you call it? The spans, clear span in the
Span.
bridge.
Yes,
Huh?
sir.
If you
Yes, sir.
see,
Thanks, sir.
yeah, yeah, good, fine, good question.